we are going to develop the vector calculus operation of curl. And so that it won't be just a mathematical abstraction, we're going to develop it starting from Ampere's circuital law. And so in the process, we'll end up getting Ampere's circuital law in point or differential form. Let's consider a small closed path. And the surface area of this path is going to be delta S. Now, if our direction of integration is in the direction of this arrow, if you put the fingers of your right hand in the direction of the integration, the direction of your thumb will define this unit vector A sub n. So let's apply Ampere's circuital law to this path. So our path of integration is indicated by this arrow here. So we'll integrate h dot dl in that direction. So if you put your fingers of your right hand in the direction of the integration, your thumb points in the direction of the current enclosed. So the current enclosed by this path will be equal to the current density in the direction of this unit vector A sub n times the surface area of the path. Okay, so now let's divide both sides of this equation by delta S and take the limit as delta S goes to 0. So the right-hand side just becomes the current density in the direction of our unit vector A sub n. The right-hand side becomes the component of the curl of H in the direction of our unit vector A sub n. And this operation of curl of vector H is written with this nomenclature, curl of H, so we want the component in the n direction is equal to J sub n. And later on in part 2, we'll understand this nomenclature of del cross H representing the curl of our vector H. Now, this will just give us the component in the n direction. Now, if we had oriented our loop such that the unit vector normal to it was in the A sub x direction, we would have found the component of the current density in the x direction. So the process to find the three components of the curl of H would be to take three surface areas, one where the normal is in the x direction, one where it's in the y, and one where it is in the z direction, to find our components of the curl of H in the three unit vectors in our coordinate system. So the curl of H would just then give us the total current density. And this is Ampere's circuital law in point or differential form. Okay, so now we have a conceptual understanding of what the curl operation is, and we should have some physical feeling for the curl of something, looking specifically here at the case of Ampere's circuital law. Okay, we still need to know how to actually perform this operation. For instance, if we're given some H, how do we actually take the curl of H to get the current density? And that's what we will cover in part 2.